The summer of 1944. A muddy field near Isigny-sur-Mer, Normandy. 3 captured German Panther tanks, imposing and silent, served a grim purpose. Targets. Lined up against them, the finest anti-tank guns the US Army had in the European theatre. General Eisenhower and other Allied commanders urgently needed answers to a terrifying question. The accepted wisdom of combat stated the Panther's frontal armor was impenetrable to standard Allied guns at typical ranges. German crews banked their lives on this math. They believed the steep slope of their glacis plate rendered them invincible. But on this July afternoon, the math broke down. The shells didn't just penetrate, they shattered the German steel like glass. The very physics of the battlefield had shifted, revealing a catastrophic intersection of desperate metallurgy and American industrial might. For the first month of the Normandy campaign, the German Panther tank was a tactical nightmare for Allied armor. Its design relied on a concept that was technically sound: 80 millimeters of steel angled at 55 degrees. This slope effectively doubled the steel's thickness to an equivalent of 140 millimeters. Standard American 75 mm and even the newer 76 mm armor-piercing rounds simply bounced off, forcing US crews into lethal flanking maneuvers against a superior enemy. But the equations changed with the introduction of a scarce, highly classified projectile, the high-velocity armor-piercing round, or HVAP. Today, we're dissecting the systemic failure of the Panther's protection in the summer of 1944. We'll examine the physics of the US Army's hypershot, the grim reality of the Isigny firing tests, and the hidden metallurgical flaw deep within the German steel. A flaw born from strategic bombing and resource starvation that transformed the Panther's greatest strength into a brittle, deadly liability. To grasp why this failure so shocked the German High Command, one must first understand the premise of the Panther's invincibility. It wasn't just a thick tank, it was a geometrically optimized survival system. When a projectile strikes a plate at a 55-degree angle, it doesn't just travel through the 80 mm thickness. It must traverse the diagonal, the line of sight thickness. Trigonometry dictates that 80 mm angled at 55 degrees presents approximately 139 to 140 millimeters of steel to a horizontal projectile. For General Fritz Bayerlein of the Panzer Lehr Division, this geometry was the bedrock of his tactical doctrine. He knew that the standard American M62 armor-piercing capped ballistic capped APCBC shell, fired from a Sherman, carried enough kinetic energy to penetrate perhaps 90 or 100 millimeters of flat steel at combat ranges. Against the effective 140 millimeters of the Panther, the American rounds were mathematically impotent. This created a psychological shield as strong as the physical one. German crews operated with the confidence that they could expose their frontal armor to enemy fire while lining up their own lethal shots. This was the Panther gap, the distance where a Panther could kill a Sherman, but a Sherman could not touch a Panther. The US Ordnance Department was keenly aware of this disparity. Their standard solution, the 76 mm M1 gun, was an improvement, but it still relied on traditional steel shot. The standard M62 projectile weighed roughly 15 pounds and left the muzzle at 2,600 feet per second. While adequate against the Tiger I's flat armor, the M62 suffered against the Panther's slope. The physics of the impact often caused the soft steel cap of the American shell to deform unevenly on the slope, inducing a yaw that robbed the penetrator of its energy, causing it to ricochet harmlessly into the sky. By early July 1944, reports from the hedgerows were grim. US crews watched their rounds shatter or bounce, while the Panthers held their ground, treating the incoming fire with disdain. The premise of the Panther held true: the system was working. However, a solution had been in development, though it was critically short in supply. This was the T4 shot, later standardized as the M93. It was known to the crews simply as HVAP, High Velocity Armor Piercing. The philosophy behind HVAP was a radical departure from the heavy steel slugs used previously. Instead of a 15-pound steel projectile, the HVAP round was essentially a delivery system for a much smaller, denser dart. At its heart lay a core of tungsten carbide, a material nearly twice as dense as steel and significantly harder. This core was wrapped in a lightweight aluminum body or windshield. Because the total projectile weight dropped from 15 pounds to roughly 9 pounds, but the propellant charge remained powerful, the laws of physics took over. Velocity is the squared variable in the kinetic energy equation. By dropping the mass, muzzle velocity skyrocketed from 2,600 feet per second to 3,400 feet per second. When this tungsten dart struck the Panther, two things happened. First, the lightweight aluminum body stripped away. Second, that incredible velocity was concentrated onto the tiny surface area of the tungsten core. It is the principle of the stiletto heel versus the boot. The same force applied to a smaller point creates catastrophic pressure. The tungsten did not try to smash the armor, it pierced it. The flaw in this system was not ballistics, but logistics. Tungsten was a strategic material vital for machine tools to build the very tanks fighting the war. Much of the Allied supply came from neutral Portugal, creating a strategic bottleneck that complicated production. The US War Production Board was stingy with its allocation. In July 1944, these rounds were handled like gold bullion, often issued only 2 or 3 per tank, if at all. But where they were available, they changed the equation. The velocity was so high that it reduced the time of flight, flattening the trajectory. The gunner didn't have to calculate elevation as precisely. He simply put the crosshair on the target and pulled the trigger. The invisible flaw of the Panther was assuming the enemy would continue to throw steel rocks when they had begun throwing tungsten darts. The theoretical effectiveness of HVAP needed to be proven in the field. This led to the Isigny tests, conducted between July 12 and July 30, 1944. This was not a laboratory experiment. It was a field tribunal presided over by General Eisenhower and General Bradley. They lined up 3 captured Panthers. Facing them were Sherman tanks equipped with the 76mm gun, the 17-pounder British Firefly, and M10 tank destroyers with their 3-inch guns. The question was simple: at what range does the Panther die? First, they fired the standard M62 ammunition. The results confirmed the crew's worst fears. At 1,000 yards, bounced. At 600 yards, bounced. Even at 200 yards, the standard American rounds failed to penetrate the Panther's glacis plate. The slope was doing its job. Then they loaded the HVAP. The range was set to 800 yards. The gunner fired. The tungsten core struck the 55-degree plate. It did not bounce. It bit. The sheer velocity overcame the tendency to ricochet. The Isigny report noted that at 800 yards, the HVAP round could penetrate the glacis plate of the Panther. But the observers noticed something else, something that wasn't supposed to happen. When the round struck, the German armor didn't just yield, it cracked. Large, jagged fissures radiated from the impact points. In some cases, entire sections of the plate broke away. This was not the behavior of high-quality armor plate, which should be ductile enough to absorb energy without shattering. This revealed a variable that Guderian and the German High Command had ignored. They assumed their tanks were made of the same high-quality steel that had conquered France in 1940. They were wrong. The failure of the Panther armor was not just a victory of American tungsten. It was a symptom of the collapse of the German industrial system. To make armor plate that is both hard enough to resist penetration and tough enough not to shatter, you need specific alloys. Molybdenum and manganese are essential to refine the grain structure of the steel, giving it ductility. By 1944, the Allied blockade and the loss of access to resources had starved the German steel industry of these critical metals. Krupp Steel and other German manufacturers were forced to improvise. They substituted vanadium or increased the carbon content to maintain hardness. High-carbon steel is very hard. It tests well on the Brunel hardness scale, but it is also brittle. It lacks the ability to deform plastically under extreme stress. When the high-velocity American round struck this brittle steel, the armor could not absorb the shock wave. Even if the round didn't fully penetrate, the energy transfer was so violent that the back of the armor plate, the side facing the crew, would explode inward. This phenomenon, known as spalling, turned the tank's own armor into a shotgun blast against the crew. The Isigny tests showed that the Panther's glacis was failing structurally. The welds were cracking. The plates were shattering. The verdict was clear. The Panther was a formidable design, let down by the reality of a failing war economy. It was designed for a war Germany could no longer afford to fight. Built with materials they no longer possessed, to withstand physics they could no longer counter. The Isigny tests changed tactical doctrine in Normandy. They proved that the Panther could be killed, provided the crews had the right ammunition. The HVAP round was a technological bridge that allowed the Allies to push through the hedgerows in Operation Cobra, negating the German advantage in armor thickness. Weeks later, at the Battle of Araucourt in September 1944, American armor equipped with HVAP rounds would validate these test results in actual combat, destroying multiple Panthers and confirming the weapon's battlefield effectiveness. It was a system failure in the truest sense. The German reliance on a single variable, armor slope, collapsed when faced with the combined weight of Allied logistical superiority and the degradation of their own industrial base.